Engineering Thermodynamics 1, Chapter 5, Lecture 1. So in Chapter 5, we extend the Chapter 4 material to consider systems in which mass is allowed to flow in and out of the system boundaries. So first thing to talk about is what's known as conservation of mass. So mass-like energy is conserved property. It can't be created or destroyed during a process. Chapter 4 again dealt with closed systems. These were systems where the mass remains constant during a process. In Chapter 5, we're going to look at systems where mass can flow across the boundaries. So we have to keep track of the amount of mass entering and leaving the control volume. The amount of mass entering through a cross-sectional area per unit time is called the mass flow rate. The mass flow rate through the entire cross-section area of a pipe is obtained by the following equation, where we integrate the density times the velocity times the differential area. Now, in general, in this class, we will not actually be integrating this formula. We're going to look at this and solve this using a very simple kind of analysis. So in general, in a pipe, such as cross-section area of a pipe shown, the velocity is going to vary. It's going to be the greatest in the center of the pipe, and it's going to be less at the edges of the pipe, and this is simply due to friction. Friction at the edges causes the mass to not flow as great as it does in the center. So the way we're going to treat this is we're going to treat this kind of approximate it where the mass flow rate is the same in all areas of the pipe. So for example, we're going to look at it like an average, kind of like an average flow rate. So the average volume flow rate is the velocity times the area. This flow rate is the volume flow rate through a cross-sectional area per unit time, and it makes this kind of problem easier to deal with. So a couple of formulas for you to look at. One of them specifically here, if we take the velocity to be a constant, we can pull this outside of the integral, and we can write this mass flow rate as density times the velocity times the cross-sectional area. We can also write the mass flow rate as the density times the volume flow rate, which is V dot over V. So here, V, remember, rho is the density. This V is the reciprocal of the density. This is what we get out of the property tables, this value here. So what do we need a control volume, and what is a control volume? Well, the problem with fluids is that it's very difficult to keep track of the millions of individual particles that comprise a fluid. It's impossible, in fact, to do it in any kind of practical way. So when we apply Newton's second law, F equals ma, which we learned back in our physics courses, here m is the mass of a solid object, a individual particle. This would be very difficult to deal with fluids because there's just too many to keep track of. Instead, what we do is we utilize the concept of what's known as a control volume and a control surface. So example A here shows what's known as a fixed control volume. So say we have a pipe and we have water flowing through the pipe from left to right. We're going to analyze this flow rate by looking at what comes through the left surface. So this would be the control surface on the left, and we'll also have a control surface on the right. It'll have a top control surface and the bottom control surface. So the control surface is sort of like the boundaries of our what make up the control volume, which is what everything is inside. So we can have particles coming into the control volume and exit the control volume. Part B here shows what's known as a moving control volume. So if you have a rocket flying, obviously you have particles being ejected from inside the little red area. So here we're going to make our control volume this little red area, and so you have particles coming out, this red area physically moves with the rocket. Where in part A it's fixed, it doesn't move at all, it's attached to the pipe. So again, a control volume is a selected volume of space within a system of particles. The boundary of this control volume is what's known as the control surface. A portion of the surface of this volume may be open, where the fluid particles flow into or out of the control volume, and the remaining portion may be closed. So conservation of mass. So when we deal with conservation of mass, For a control volume, what we're looking at is we're looking at the total mass entering the control volume during a certain period of time, minus the total mass leaving the control volume during a period of time. That's going to equal the net change within the control volume. So we can write this as an equation saying M in minus M out equals change in mass of the control volume. Or if we want to deal with rates of flow, we can talk about M dot N. So this is a mass flow rate, kilograms per second. In minus the mass flow rate out equals the time rate of change of the mass entering the control volume. So we can write this in a most general way using an integral. But in our case, in our dealings, we're going to look at this as the time rate of change of the mass from the control volume equals the sum of the mass flow rate in minus the sum of the mass flow rate out. So here, for example, if you have a tub, and say we're filling the tub, we have 50 kilograms coming in. Let's say this is, in our book, he just shows us as 50 kilograms, so he's dealing with just the mass. So you got 50 kilograms coming in, you got 30 kilograms coming out. The change in mass in the bathtub is mass in minus mass out of 20 kilograms. Now, if you had, 50 kilograms coming in per second and 30 kilograms going out per second, this would be a 20 kilogram per second change in mass rate inside the tub. So this is just keeping track, kind of like budget keeping, of what comes in minus what comes out, and to keep track of how much the mass is changing within our control volume. So mass balance for steady flow processes. So during a steady flow process, the total amount of mass contained within a control volume does not change with time. So, and this is typically the kind of case we have in industry, where we have a plant, a steam plant, for example, up and running. You'll have steam coming into the system. You'll have condensed water going out of the system. But the rate will be the same. So what comes in will actually come out. In other words, the change in mass in the control volume is going to be 0. You'll have just as much come in as go out. In that case, it becomes very easy. The equation on the previous slide reduces to the following that I'm highlighting here. The sum of the change in the mass flow rate equals the sum of the change out of the mass going out. So in the case of a very simple system where you have a single stream, you have, for example, this one shows 2 streams. You have one coming in, M1, and you have M2 coming in, and you have M3 going out. If you just had one single pipe, this would be M1 dot equals M2 dot, or rho 1 V1 A1 equals rho 2 V2 A2. Now, in the example that the book shows, you would add, you would have the fact that you would have M1 dot plus M2 dot equals M3 dot. So you'd have a slightly different equation for that. And so this is where the multiple inlets and exits equation comes in very nicely. So, in a lot of cases we deal with in engineering, are devices we make, such as nozzles, diffusers, turbines, compressors, and pumps. They only involve a single stream, one inlet, one outlet. So they're very easy to kind of deal with, or easier to deal with. So let's take a look at example 5.1. A garden hose attached with a nozzle is used to fill a 10-gallon bucket. The inner diameter of the hose is 2 centimeters, and it reduces to 0.8 centimeters at the nozzle exit. If it takes 50 seconds to fill the bucket with water, determine the volume and mass flow rates of the water through the hose and the average velocity of the water at the nozzle exit. So here we can sort of just apply the equation. The volume flow rate is the volume divided by the change in time. So 10 gallons divided by 50 seconds. And then, our book here, he wants us to put this in liters per second, so we can use the conversion factor and come up with 0.757 liters per second. Then we can apply for the mass flow rate, it's the density times the volume flow rate. So the density is 1 kilograms per liter, which we're told that that's just the density of water, times the volume flow rate. So you get 0.757 kilograms per second. Now we can find the velocity because we know, for example, that the velocity equals the volume flow rate divided by the area. So we can find the area because it's a circle, so it's pi r squared. So, and we're told that it's 0.4 centimeters. So pi times 0.4 centimeters squared. Then we can divide that into the volume flow rate we found. We can get 15.1 meters per second is the velocity of the water at the nozzle exit. So special case is what's known as incompressible flow. In this case, the concentration and mass relations can be further simplified because the density can cancel out on both sides. And this is usually the case, as our book points out, it's for liquids. So it doesn't work for gases, but for liquids it works really, really well. We can rewrite this equation as the volume flow rate in equals the volume flow rate out. So if you have a single stream, it's just V1 dot equals V2 dot, or V1A1 equals V2A2. So for, and as our book points out, there's really no such thing as a conservation of volume principle. However, for steady flow of fluids, the volume flow rates as well as the mass flow rates remain constants, since liquids are essentially incompressible substances and the densities cancel out on both sides of the equation. So let's talk about flow work and the energy of a flowing fluid. So as we know from our studies of physics, we have when we classify energy as either kinetic energy or potential energy. Well, there's another sort of energy involved that we find very useful, which is known as what's known as flow energy or flow work. So back from physics, we know that force equals pressure times area, and work is defined to be force moved through a distance, F times L. So if here, for example, let's say we have an imaginary piston, and it's going to push on a chunk of fluid. The chunk of fluid has a certain volume, a certain pressure, and a certain mass. We take our piston and we push this fluid a distance L. So how much work did we do? Well, we did F times L, but F, remember, is our pressure times our area. So A times L, that's our volume, so pressure times volume. So here we're going to define this as, if we divide through by the mass, and we'll write this as a workflow per unit mass is the pressure times the reciprocal of the density, right? And again, this is what we get out of the property tables, the V values we get. So, this is a very useful principle and we sort of know this from just intuition alone, because we know a moving fluid can certainly do work. It can certainly push things. It can shove things. It can tear things up. We see this every time there's a storm, and there's and the water rises. If you live near a river, you're very familiar with the water, the damage that can occur to the moving water. So the total energy of a flowing fluid we can come up with pretty easily, because, so for example, E, which we've talked about as the energy per unit mass, it consists of the internal energy, U, plus the kinetic energy, plus the potential energy. So kinetic energy is V squared over 2. Again, this is kinetic energy per unit mass, so the M is divided out, plus G times E. This is the potential energy term. Now, if we add to this E, we add the flow work, pressure times the specific volume, the small v, we get the PV term plus all the terms from up above. However, U plus PV, we know what that is. That's the enthalpy, H. And again, H is in the table. So we can write this theta, work for the flow energy, as H plus the kinetic energy plus the potential energy. So here's the equation written as we'll use it in this particular chapter. So this here shows a little example. So for a non-flowing fluid, you have the internal energy plus the kinetic and potential. For a flowing fluid, we combine the flow energy plus the internal energy, and typically write this as H, the enthalpy, plus the kinetic energy term plus the potential energy term. So we could also talk about, how much energy is transposed, because if we, theta again is the energy per unit mass, so we just multiply by the mass, we'll have the total energy. If you multiply by the mass rate, then you end up with the rate of energy transport, E dot, energy per unit time being transported. Now, typically, in a lot of our systems we'll deal with, the kinetic energy and the potential energy terms are negligible. So this reduces down to two very simple equations. The energy is just m times h, and the energy flow rate is m dot times h. So let's take a look at an example. Steam is leaving a 4-liter pressure cooker whose operating pressure is 150 kilopascals. It's observed that the amount of liquid in the cooker has decreased by 0.6 liter in 40 minutes after the steady operating conditions are established. The cross-sectional area of the exit opening here, you can see in the diagram, is 8 square millimeters. Determine the mass flow rate of the steam and the exit velocity, the total and flow energies of the steam per unit mass, and the rate at which energy leaves the cooker by steam. So here we can look up the properties of, we're dealing with water, so it's a saturated liquid vapor. At 150 kilopascals, we can look in the property tables, and we can find the specific volume F and the specific volume G, the VF and VG values. We can find the UG value. We can find the HG values. Again, these are right out of the table. And we'll need this in parts B. So first of all, in part A, we can calculate the mass, because the change in liquid we're told is 0.6 liter. We can divide that by the specific volume, VF value. So we can find that it's 0.570 kilograms. And again, here's the conversion factor. We've got to convert from liters to cubic meters. So m dot is just this mass divided by the time. So again, we can convert this to our standard kilograms per second here. Here we can find the velocity flow rate, which is m dot divided by rho times the area. And again, so this is the velocity of the steam leaving. So again, we're dividing by the density of the steam. So we can find this, but this is easy to invert the rho g and make this the specific volume at g value, which again we had that in the table. That's the VG value here. It's easy to forget that the relationship between density and specific volume is they're reciprocal. So VG is 1 over rho g. So we know what the m dot is. We found that. VG is given here. And we can divide by the area which we found in the previous slide. So part B, here we can calculate the energy flow rate because it's just PV, since we're ignoring kinetic energy, potential energy. So this is H minus U. And these values, we can look these values up. We had those looked up, so we find what the energy is. And the theta value we can find, because we're ignoring the kinetic energy potential, that's just the H value. And here he does note that the kinetic energy term is so much smaller compared to the enthalpy that it's not worth considering. We can find the rate at which energy is leaving the cooker. This is just E dot, which is m dot times theta. M dot we found, and then we can multiply that by theta, which we found here, to find 0.638 kilojoules per second. And so a kilojoule per second, that's a kilowatt. So our answer is 0.638 kilowatts. So let's look at some energy analysis of steady flow systems. So again, these are systems where you have mass coming into the system, you have mass going out of the system, but inside the control volume, which is again inside the little dotted line, the mass remains constant and the energy remains constant. So many engineering systems, as power plants, operate under these kind of steady flow conditions. Once the plant started up and got up to power, it operates continually at a steady rate because you're trying to, for example, if you're trying to make electricity, the power plant's going to operate at its capacity to maintain the power grid, so they can send power to our homes. You don't want that fluctuating. So under steady flow conditions, the fluid properties at the inlet and exit remain constant. They don't change with time. So if you have, for example, you have an inlet and two outlets, well, you have mass coming in, mass flow rate coming into the system. You have a certain amount of enthalpy coming into the system, and you have a certain mass flow rates out of the system here, m.2, m.3, and H2 and H3 are the enthalpies coming out of the system. So the fluid coming into the system has this much enthalpy, and here, for example, this device, there's two ways for the fluid to flow. It flows this way and that way. So you'll have H2 and H3, the energy coming out of the system. So in general, these kinds of balances, which we've talked about before, you can write this, for a very simple system where you have like a water heater where you have, here cold water coming in at a certain flow rate, a certain temperature. It's heated up by the heating element, and it comes out at a hotter temperature. But in general, the mass flow rate in equals the mass flow rate out. If 1 kilogram per second of water comes in this way, 1 kilograms per second goes out this way. You wouldn't want it building up inside of the hot water tank. Inside the control volume, you have a certain amount of work that you're putting into it. This is typically either due to electrical work, or it's if you have an electrical water heater, or it's a flame if you have like a natural gas kind of water heater. And Q dot out is simply the heat loss out through the casing to the environment. So we can talk about the mass balance, which we talked about. We can talk about the energy balance, but in general, under steady flow condition, the amount of energy coming into the system is going to be the amount of energy going out of the system. So here we can write this general kind of equation for Q dot in plus work in plus these terms here is for each inlet. So this is your m dot times your H plus the kinetic energy term plus the potential energy term. This is coming into the system, and going out of the system, of course, you have a kind of mirror image of these kind of terms. We'll have a Q dot out, a work dot out, and this was the flow energy going out of the system. Now, a lot of cases, a lot of these terms will be zero. So, for example, in this example here, you really don't have a Q in. That term is going to be zero. You really don't have a work out. That term is going to be zero. And typically, on both sides, the kinetic energy, potential energy terms will typically approximate to be zero because the enthalpy is going to be so much higher. We'll find in a couple of problems he actually works through these, and he shows you that you can take this into account, but H is so much bigger than the V squared over 2 or the GZ that it's negligible. So here, when solving these kinds of problems that involve an unknown heat or work interaction, we'll go back to the approach we used before to assume that heat to be transferred into the system and work is produced by the system. We'll assume those kind of be positive. Then a negative quantity is for the work or heat. It simply means that the assumed direction should be reversed. So in other words, if you solve one of these and you get a negative, that just means that then instead of coming in, it actually went out. These equations get a lot simpler for single stream devices, which are defined as only having one input and one output. In that case, you kind of get rid of the sums, and this simply reduces down to the following equation. The bottom one is simply taking the top one and dividing through by the mass. This is the table that we often use because, again, these H values here are in the tables. And again, this term and that term typically are negligible. Unless we're dealing with nozzles, and we'll have to use this one here, and I'll show you that later on. So now let's take a look at a few examples, and these are actual devices. So we're going to take that previous equation that we developed, and we're going to solve for specific engineering devices. So for example, the first one, let's look at nozzles and diffusers. Well, first of all, there's nozzle and diffuser are very, very related. So in a nozzle, the velocity, let's say we have a nozzle like on our hose at home. So what that does is, you have the water coming into the nozzle and the water coming out of the nozzle. Well, for a nozzle, the water velocity coming out is going to be much, much bigger than what's coming in. A diffuser, on the other hand, is actually the opposite. What it does is it makes the water coming out much less than the water coming in. So these are commonly used in jet engines and rockets and even garden hoses, like the example I talked about. So if you look at it, again, from a conservation energy point of view, the amount of energy coming into the nozzle equals the amount of energy coming out of the nozzle. In this case, we do have to keep the kinetic energy term because that's actually the purpose of the device, is to change the kinetic energy. So coming into the nozzle, you'll have m dot times h1 plus v1 squared over 2. Coming out of the nozzle, you'll have m dot times h2 plus v2 squared over 2. In this case, again, we're assuming the kinetic energy and potential energy and the work term are all 0. And so, this is a very easy equation to solve. So we'll look at a couple of examples of this in a little bit later. So here's the first example. So here we have air at 10 degrees C and 80 kilopascals enter a diffuser of a jet engine steady with a velocity of 200 meters per second. The inlet area of the diffuser is 0.4 square meters. The air leaves the diffuser with a velocity that is very small compared to the inlet velocity. Determine the mass flow rate of the air and the temperature of the air leaving the diffuser. So here, all air enters the diffuser steadily at a specified velocity. The mass flow rate of the air and the temperature of the diffuser are to be determined. That's what we're trying to find. So here we take the diffuser as our system, and since there's only one inlet and one outlet, a certain mass comes in, a certain amount comes out. So instead of talking about M1 and M2, we can they're both equal. So we'll just set it equal to M dot. So to determine the mass flow rate, we need to find the specific volume of the air first. We can do this from the ideal gas relationship because, again, it's airs and we're treating air as ideal gas. So the specific volume is RT over the pressure. So look back in the last chapter if you don't remember how to use the ideal gas law here. Here's the ideal gas law constant. The temperature we have to plug in has to be the absolute temperature. Here's the pressure, so we can calculate the specific volume. Then the mass flow rate is simply easy to calculate. Again, we can look up the V1 we calculated. The velocity is given, the area is given, so we can calculate the mass flow rate. So since the flow is steady, this mass flow rate is the same coming in and coming out of the diffuser. So under the stated assumptions, the kinetic energy balance can be expressed in the following form. And since the m dot is the same on both sides, we can sort of just cancel that out. We can solve this for H2. H2 is equal to H1 minus this change in kinetic energy terms. So I've just repeated this at the bottom of the slide up at the top so we can sort of see what we're doing here. So here, we can look up what the enthalpy is, table A17, at 283 Kelvin. We can look that value up. So we can actually calculate what the enthalpy is on the exit. Because we're told what the inlet and outlet velocities are. So if you look back in table A17, you can look up this enthalpy value and find that the temperature associated with that enthalpy is 303 Kelvin. So what does that mean? Well, it means that the air increased about 20 degrees C as it went through the diffuser. Let's look at another example. This is acceleration in the steam of a nozzle. So here we have steam at 250 psi, 700 degrees Fahrenheit, has an inlet of the nozzle is 0.2 cubic feet. I'm sorry, 0.2 square feet. And the outlet is 200, the steam comes out at 200 psi and 900 feet per second. He tells us that heat loss through the casing is 1.2 BTUs per pound mass. He wants us to find the inlet velocity and the exit temperature of the steam. So here again, since there's only one inlet and one outlet, we're gonna just instead of having M1 and M2, we're gonna have you just treat it as M. So M dot is equal to 10 pound mass per second, which we were told flows in and flows out. So that stays constant throughout the system. So at the inlet, nozzle inlet, we can look up that we're told the pressure, we're told the temperature. So we can look up the specific volume and we can look up the enthalpy out of table A6E. So again, I encourage you to go look in the table and just get used to finding these values. M dot, we can calculate that. We know what M dot is. So here we don't know the volume, the velocity, V1, but we can find it because we know everything else. We know M dot, we know the area, we know the specific volume. So we can solve this for V1. So we get 134.4 feet per second. So under the stated assumptions, we conserve energy. So we have the energy at the inlet equals the energy at the outlet. And here we do have a Q dot out term that we're told. Since M dot is the same, we can just divide through by it. So it goes away here, it goes away there. Q dot out over divided by M dot, that's small q out. So each of these terms we can sort of look up. We know what H1 is. We know what Q dot is. We know the velocities. So we can calculate what the H2 is. And then we can go back in the table because we know what the pressure is coming out, and now we know the enthalpy. We can go back in the table and find what the temperature is. And again, I encourage you to look this value up yourself. And find what this value is. So let's look at the table here. So just to show you how to do this again. So here we find that, if you look in the table, you'll find that we have to be in the superheated table. So if you go to the superheated table at 200 psi, and you look up, you go down through the list here, and you're looking for H, right? So here's your H column. So if you go down here and look for 1354, obviously you don't find the exact value in here. So it's somewhere between here, so your temperature is somewhere between 600 and 700 degrees Fahrenheit. So what you're going to have to do here is you're going to have to interpolate. And again, you have to practice the interpolation skills. Use your calculator. So if you interpolate, you find that the temperature is 662 degrees Fahrenheit. So this is the end of this slide. In the next slide lecture, we'll look at turbines.